Thank you both for the introductions. And thank you everybody for getting up early on, I guess, Monday evening or something like that. But I realize how hard it is for academics to get up at such an unreasonably early hour. So I appreciate that you are all coming here. And now I guess is the time when I drive you all the way by telling you sort of, which things I'm going to assume that you know, although I'm going to try to sort of build up slowly. But let me share my Blackboard. Okay, so the title of the talk is, or of the lecture series is the non-commutative geometry of difference equations. And as I said in my abstract, or at least tried to convey in my abstract, mostly what I'm actually going to be talking about is going to be commutative geometry, so just regular old familiar, in Hartshorne algebraic geometry. I'll touch a little bit on what happens when things become non-commutative and why we want things to become non-commutative. But it turns out that you can actually you can get a lot of information, and especially you can get a lot of ideas on the integrable system side by just understanding the commutative geometry of the picture. So that's what I'm mainly going to be focusing on. Now, this is based on a possibly not horribly non-random sample of the Japanese mathematicians I know who are definitely, definitely know integrable systems, definitely know algebraic geometry, or at least mostly know algebraic geometry, and have never seen non-commutative geometry before. Although that last, I think, is also most people. Non-commutative geometry, especially when you take into account that there's like 3 different kinds of non-commutative geometry out there, is definitely not as widely known as the others. And so since I'm trying to keep this reasonably accessible for as long as I can, that's pretty much what I'm going to be assuming. Also, I've heard I guess the title of this overall program at RIMS is involving differential geometry. I don't actually know much differential geometry. So, and in fact, one of the big reasons why I went into the non-commutative geometry side of things is so I didn't have to understand the differential geometry stuff. So, but anyway, so let me start by telling you a little bit about where this is coming from. So what was my motivation? So the motivation is that there are these integrable systems called the Painlevé transcendents, or the Painlevé equations. And they come in a bunch of different flavors. In particular, the best classification of them, once you start taking into account fancier versions of them. I mean, of course, they were originally classified by Painlevé, and then I believe it was Garnier who pointed out that Painlevé made a mistake and missed one or something. But by this very odd sort of complex analytic criterion. And then I think it was Picard or Fuchs, I think, who later realized, hey, there's a slightly better way. I'm probably mangling this, but anyway, but they were there are these particular nonlinear differential equations, second order, and then people started realizing, hey, there are some nice things you can do if you can discretize them and have them still behave well. And they started building up these discrete hierarchy. And then finally, the full hierarchy was classified by Sakai using algebraic geometry. In particular, the algebraic geometry of projective surfaces, and in particular, projective rational surfaces. And so that, pretty much explained all the discrete Painlevé equations, except for one thing. So I mentioned Painlevé had his own way of understanding things, and that's actually what Sakai generalized. But there's another way of getting at them, which is really what explains why they show up in practice. So where do Painlevé come? Where do the Painlevé equations come from? Incidentally, the reason I'm not writing down a Painlevé equation is because they're all horribly complicated, except for the ones that are very, very low level. And one of the weird things about this, the algebraic geometric perspective that I have, is that the more degenerate it is, the harder it is for me to think about it. And so the ones that are degenerate enough for me to think about are so degenerate I can't think about them, or at least I can't easily think about them. And so I never actually write them down. But where do the Painlevé equations come from? Well, so where they really come from is they're flows in families of differential equations. And so let me start by actually something that's not Painlevé, but starts to get the flavor. So Gauss, introduced the hypergeometric functions, and in particular, the hypergeometric equations. And these are also, too complicated to really write down, but they have a very nice description. I mean, of course, you can write them down, but it takes time and everything. So how do you describe the equation? Well, it's characterized by the following. Firstly, it's a second order Fuchsian and linear ODE. It has 3 singular points. So in particular, anytime somebody gives you 3 points in the complex plane, they're always going to be 0, 1, and infinity. So singular is 0, 1, and infinity. And it's Fuchsian. And so the only other thing we need to do to sort of specify what the equation is locally is we specify the exponents. Around the singular points. So basically, the way to think of this, if you're less familiar with ODEs, is if you try to solve the equation, at a generic point, it's a second order equation, you get a 2-dimensional space of solutions. But as you approach one of the singular points, well, of course, it's still a 2-dimensional space of solutions, but the asymptotic behavior is going to depend on very much on what your solution is. And particularly what you find is that there's a sort of big solution that sort of gives you the dominant asymptotic behavior. And because this is a Fuchsian equation, what that basically means is that the dominant behavior is going to be some power of z as you approach, or let's say we approach 0, it's going to be some power of z. But then there's going to be another solution which has a different asymptotic, and that's going to be a different power of z. And so when I talk about the exponents, I mean those 2 powers of z. And one of the things is that you can read that off from the actual equation. And I'll talk a little bit more about that. Okay. And the beautiful thing about Gauss's hypergeometric equation, which I believe was noticed by Riemann, is if I tell you the exponents around the 3 singular points, that uniquely characterizes the equation up to changes of basis. So in particular, we get an equation. Now, whenever I talk about an equation, a differential equation, and what I always mean is matrix form. So A is a 2x2 matrix with rational coefficients. And the structure that I said before says that A has simple poles at 0, 1, and, well, infinity, with a big footnote saying that what it means to be a pole of an equation infinity, you have to actually do the change of variables, and then it's a pole of the equation of 0. And the exponents are the eigenvalues of the poles, of the residues. Which, it's a simple pole at these 3 points. So the residue is a matrix, and so you take the eigenvalues. And then it's not too hard to see that the asymptotic behavior of the equation as you approach the singularity is determined by the eigenvalues of the residues, at least the leading terms. Okay. So, and now we can sort of pretend we're doing algebraic geometry, and we can just sort of count how many there ought to be. So, okay. So firstly, it has simple poles at 0, 1, and 1 and infinity, nowhere else. And this tells us in particular that it's, it's going to look like A0 over T plus A1 over T minus 1, such that A0 plus A1 is, well, it's going to be equal to 0, because the pole at infinity would be basically the pole at infinity would be a double pole if it wasn't equal to 0. And so now we count this, and we say, okay, well, that means that we have 2 matrices that gives us 8 such. So this is what A is. I guess I switched to T. Okay, so there are 8 such matrices before we specify the exponents. Okay, now beyond that, what else do we know? Well, the other thing we know is that there are, well, I've only specified this up to changes of basis. And it's a 2 by 2 matrix. So there are 3 changes of basis we need to subtract. Okay, and then we're specifying the 6 eigenvalues, 2 eigenvalues for each residue. So what is that? Well, we're specifying, to specify the eigenvalues, you can specify the characteristic polynomial. So we're specifying the characteristic polynomial of A naught, of A1, and of A infinity, which is some combination of A0 and A1 that you get by doing the change of variables. So, okay, so they're specifying 6 conditions. That's great, and that gives us -1 things, which is a little annoying. However, we then realize that 3 of our conditions were not independent, because the trace of A is an honest to goodness rational function. And the sum of the residues of a rational function is always 0. So we lose 1 condition because it's redundant. So the condition, so basically if you separate the characteristic polynomial into a condition on the trace, a condition on the determinant, the conditions on the traces are redundant. And so we get 0. And so this tells us that if you believe this dimension counting, there should be a unique equation. And you can actually do the geometry, and it'll follow as an easy consequence of the general theory that this really is a 0-dimensional space. In particular, you get a unique equation up to these changes of variables. And this is with some genericity assumptions on the eigenvalues. Okay, so this was a warm-up. So what if we had 4 singularities? So now we can put the singularities at 0, 1, and infinity. 3. We can put the first 3 at 0, 1, and infinity. And then we have 1 more singular point, which we traditionally would call lambda. Again, if you have 4 points in C, the 4th point is always called lambda. Okay, so now our equation, assuming we still have simple poles, is going to be A0 over T plus A1 over T minus 1 plus A lambda over T minus lambda. And again, it's going to have this condition that the sum is 0. I think this is correct. Yeah. Wait, no. Sorry, I was incorrect earlier. Infinity is minus the sum of A0 and A1. So A infinity is the sum. And okay, so now we do the same dimension counting, assuming we specified now our 8 exponents. So the dimension is, okay, we have 3 matrices. So that's 12. We have, because 3 2x2 matrices, we lose 3 degrees of freedom for the changes basis. And then we're imposing 8 conditions, one of which is redundant because, again, the traces of these 4 matrices have to add to 0. It's possible I'm slightly wrong here. There should be a 2 or something, but we can pretend this is correct. Okay, so this gives us 2. So in other words, we have a 2-dimensional family now of such equations. Okay, now, okay, this is still a linear ODE. Where does Painlevé come from? Well, there's another piece of information that you get from a Fuchsian equation. So a Fuchsian equation has monotomy. So let me draw a picture. So we have, in this case, our 4 singular points. I'm going to pretend infinity is actually visible. And then what we know is that at any point, sorry, I don't think, let's try blue, that should show up better, yes. Okay, at any point, we have a 2-dimensional space of solutions. So let's fix a point that's not one of our singular points and fix a basis of solutions. Okay, well, and I've drawn it sort of out of the line because we're in the complex plane, really. We should solve everything over complex analytic. So we have 2 analytic solutions near this point. And so in particular, extend to a neighborhood. And we can keep extending. And so for any path, we can keep extending along that path. And each of our solutions analytically continues along that path. And the way you do that is, if it's been a while since you've thought about complex geometry analysis, you cover the path by small disks. And then in each small disk is analytic, as long as it's small enough it doesn't actually hit one of your 4 singular points. And then you just analytically continue your function, and general nonsense tells you it'll satisfy the same equation. So along any path, you can analytically continue and get a pair of solutions at the end of the path. And of course, what you should do is end back where you started. So now you've started with a pair of solutions. You've analytically continued along this path. And you've ended up with another pair of solutions. And the key fact is the new solutions you get don't have to be the same. And in general, won't be. In particular, it's, again, and in fact, it actually follows from the asymptotics. And this is one way you can actually compute the monotomy for if you're dealing with a complicated equation, is by understanding what's going on with the asymptotics, is that if you take a small path around one of the singular points, remember there were these 2 special solutions, the big solution and the small solution. Well, if you, and the small solution is clear, it's very special, it's smaller. And if you analytically continue the small solution around a tiny circle around your singular point, it can't possibly become big. And so it's going to remain small, but it'll become a multiple of itself. Because near that singular point, it looks like a power of z. And unless it's an integer power of z, it's not analytic at the singular point. And so it's going to get multiplied by e to the 2 pi I, that power. Okay, and then, well, now you have this other solution, this big solution. Well, it's going to be transformed to a multiple of itself plus the small solution. And then it's easy to see that that multiple has to be the other e to the 2 pi I z. And you can then make it actually an eigenfunction. So the 2 special solutions are just basically the eigenvalues of what happens when you analytically continue around a small path. Okay, but what happens when you analytically continue is a homotopy invariant. If you deform your path, it doesn't change. And so we can take this and we can just take our arbitrary starting point and recover the full information about the monodermy by starting at that point. And so what we find is that we get four, oops. We get four generators of the fundamental group, which are, well, okay, we start at our base point, loop around, we loop around, we loop around, and we loop around. So each of our singular points, we sort of take an obvious loop around, and then we just need to make sure we orient them in a consistent way. And that gives us our four generators. Okay, and assuming our, and I probably wrote the four generators in the wrong order. So assuming our singularities are 0, 1, lambda, and infinity, then we get generators which are gamma 0, gamma 1, gamma 2, sorry, gamma lambda, gamma infinity. And if you think about it, the product of those generators is 1. So basically, the point is going around 0 and then going around 1 is the same as going around both 0 and 1. And so similarly, going around both 0, 1, and lambda, or going around both 0, 1, lambda, and infinity. But this is we're really on a sphere. And so if you're going around all four of your singular points, you can just shrink in the opposite direction, in the opposite hemisphere, basically, and become trivial. So we have our four generators, and they multiply to 1. Okay. Moreover, but we know more than this, because we know the eigenvalues of each one of these loops. Namely, they're the exponentials of the eigenvalues of the residues. So gamma naught, well, it's not equal to, but it's conjugate to e to the 2 pi I a0, etc. Okay, so far so good. And so we know the 8 eigenvalues. Okay, so let's count how many solutions there are. Well, okay, the product of the matrices is known, so we only need to specify gamma naught, gamma 1, gamma lambda. They are elements of GL2, so that's a 4-dimensional space. So we get 12. We still have the changes of basis, -3. And we're still specifying 8 eigenvalues. And they're still redundant, because the product of the determinants of our four matrices is 1 because their product is 1. So we lose 1 degree of freedom from the determinant. And so that gives us 2. Okay, and then we have the fun fact, which is really important, and I don't actually know how to prove, but this is well, essentially, there are some technical issues. This is essentially a bijection from the 2-dimensional space of equations to the 2-dimensional space of monodermy representations. So to be precise, when I talk about the monodermy of the Fuchsian equation, what I mean is the representation of the fundamental group. And as usual in representation theory, when we talk about a representation, we always mean up to changes of basis. So we have a 2-dimensional moduli space, if we want to get algebraic geometric, of Fuchsian differential equations with specified singular points and specified exponents. And we have a 2-dimensional space of monodermy representations. Okay, and it's clear if I hand you the equation that determines the monodermy. The harder fact is that if you that the monodromy actually uniquely determines the equations. And there's some edge issues that arise. In particular, sometimes when you do this to your monodromy, what you get is going to be is not actually going to have a matrix form for your equation, and you have to. So there's some annoying issues there. But roughly speaking, this is what's happening. Okay, and so in particular, but then we notice one more thing, which is that the fundamental group of C minus 0, 1 lambda infinity doesn't depend on lambda. And it doesn't depend on lambda in a well-defined way, in that if we move lambda slightly, we can carry along the particular just chosen generators of the fundamental group. Because basically you started with this one particular loop around lambda. As long as we move lambda in such a way that it doesn't cross over that any of our 4 generators, we still get a generator of C minus those 4 points. And so locally, we have a constant fundamental group. And so locally, as we move lambda, we can ask for the monodromy not to change. So since pi1 of C minus singularities doesn't care about where the singularities are, we can move the singularities and ask for the monodromy to stay the same. Okay. And in particular, because this is a bijection, this actually gives us an analytic function of lambda. So if we start with one particular choice of equation and then change lambda, we get a holomorphic function of lambda, except at 0, 1, and infinity, because both 2 of our singularities come together, that actually does break the fundamental group. So we can't actually make lambda equals 0, 1, or infinity here. But what we can do is we can still talk about the monodromy of this thing. We can start with our equation, move lambda in a loop around 0, and see what happens. Okay, and this gives us a flow, an isomonodromy flow, in the space of equations, for where we basically include lambda as an extra parameter. So this is now a 3-dimensional space, and we're flowing as lambda flows. Okay. Now, the other thing we can observe is that the family of equations also doesn't depend on lambda, or it doesn't much. Because remember, what we had was we had 3 matrices, or let's say 4 matrices, we include A infinity. We had 4 matrices that added to 0, and we specified their eigenvalues. And that clearly doesn't depend on lambda. I mean, that family doesn't depend on lambda. So we can actually collapse this flow and sort of factor away lambda. And so it gives us an actual flow inside this one surface. And one can show that the surface is rational. Again, this will follow from the general theory. And so therefore, we get a second order differential equation controlling this flow. Now, the thing is, of course, this is a rational. We've chosen this rational parameterization of our surface. This is a very nonlinear thing to do. And so the second order equation will end up being nonlinear. And this is, in this case, the Painlevé-6 equation is called. Okay, so this is how one gets, and it turns out this is really what explains the appearance of the Painlevé equations in, to pick a completely random example, random matrix theory, which is where I first encountered them many, many years ago. Like 25, probably, a bit less than 25, but quite a long time ago. And because basically, well, I'll say a bit more about this later, maybe. But in any case, so this is where the Painlevé-6 equation comes from. And the other Painlevé equations are either more complicated or less complicated versions of this, depending on the perspective you're taking. They're less complicated in that they're easier to write down the nonlinear equation. They're more complicated in that the singularities are no longer Fuchsian. So you basically, if you take this picture and allow your singularities to degenerate. So for instance, if you do take the limit lambda goes to 0, then what will typically happen is that now A will have a second order pole, which means its behavior locally is more complicated. And one of the things that's always annoyed me a little bit about the terminology here is that the flows are always called isomonodermy, despite the fact that they actually have to preserve more than just monodermy. They're actually preserving the local behavior of the equation at the singular points, but in an analytic sense as opposed to an algebraic sense. So that's really what's getting preserved, is sort of the local analytic behavior of the equation at the singular points. And so if you look at how this picture degenerates, you're led to a hierarchy of different equations. And I may get this wrong, but I believe there are 8 of them, which explains why the most general one is called the Painlevé-6 equation. This is because it was not actually obvious from Painlevé's description sort of which things should be counted as the same kind. And so it turns out that Painlevé's Painlevé-3 equation actually gets split up into 3 things if you think of it in terms of the most natural classification. And in fact, actually, it's worse than that, because if we talk about in terms of this monodermy preserving flow, you actually get multiple different Painlevé equations corresponding to the same, you can get the same Painlevé equation coming from different descriptions of this linear equation. I should say, to set my terminology for later, this linear equation is either called the linear problem or the lax pair. Incidentally, it took me a while to realize that lax here is somebody's name. It's not an adjective. So strictly speaking, the lax pair is the combination of the linear problem and the information about how Painlevé acts that sort of tells you that it preserves. That's enough to tell you that it preserves the monodermy, but it's for the most part they're essentially the same. Okay, so this is the terminology. Okay, now, okay, so what this tells us is that, you know, Painlevé-6 has attached to it this lax pair, this second order linear Fuchsian equation, and we can recover Painlevé from it. And moreover, because there's this, using the geometry of the picture, the fact that there is this moduli space of equations that is flowing in, you realize that actually, Painlevé's thing comes from Painlevé's original form for Painlevé 6 comes from a particular parameterization of the surface. And it has singularities because there are places where the parameterization of the surface kind of breaks. I mean, it's not P1 cross P1. And so writing it as you have two variables is going to break. But it turns out that because it has flowing on this nice surface, you can actually recover the fact that it doesn't have bad singularities, or rather the only bad singularities are at 0, 1, and infinity. Every other singularity of any solution of the Painlevé 6 equation is a pole. So now the poles can move depending on your initial conditions, but the essential singularities, which are in this case are 0, 1, and infinity, never move. And this was Painlevé's original criterion. He was looking for second-order nonlinear equations with, I believe, rational coefficients, such that the essential singularities were independent of the initial conditions. And if you play around with nonlinear equations, this is a very strong condition. So particularly the only things that satisfy this are the Painlevé transcendents, or their equations, various equations related to them coming from elliptic curves, and then a few weird subcases like things that are Riccati, things that are basically Riccati type equations or what have you. Okay, so, and this, as I said, is what Sakai later generalized after people had come up with these discrete versions, and basically based on this algebraic geometric perspective rather than the linear problem. And so there was a problem. What is the lax pair? For these other Painlevé type equations. Now, there's another question that arises, which I've already sort of touched on slightly. Well, more of a question than a problem. Given a family of, let's say, just say still for the moment, differential equations with specified singularities, and when I say specified singularities, I mean not just where the singularities are, but the local structure of the equation near the singularities. So, is it a simple pole? Is it a double pole? What's the residue? That sort of thing. So given a family of differential equations with specified singularities, well, the first question is, when is the equation unique? If I specify, remember the hypergeometric equation was uniquely determined by having those three singularities. So when is that the case? For what systems of singularities with specified exponents or more complicated for non-Fuchsian, when is that uniquely determined the equation? And more generally, what does the family look like? And we're talking, and again, this is some sort of, we can expect this to be an algebraic geometric object. So when we say, what does it look like? What's the dimension? Is it rational? Are there nice structures on it? What can we say about the family? Okay, and in particular, one reason why this is important is if we can understand this question well enough, it lets us further generalize the Painlevé equations. Now, this was already done somewhat. I believe Garnier was one of the first. If you look at second-order equations with 5 singular points or 6 singular points, or what have you, everything I've said so far carries over. You do the dimension count, and you see that if you have if you have 3 plus m singular points, then the dimension of the family is 2m dimensional. And the dimension of the family of possible monodermy representations is also 2m dimensional. It's still a bijection. And so you still get these flows. Now, of course, they're not second order nonlinear equations, they're order 2m nonlinear equations, but you get this flow. They're called the Garnier equations, etc. But you can ask, for instance, there's this hierarchy of Pain-Levé equations. What's the corresponding hierarchy for Garnier equations? And of course, so the first step is we need to understand what the Lax pair looks like, and then we need to understand how to classify them. And that'll tell us the space on which these generalized equations are flowing. And then once we understand that, basically what is the space of initial conditions is what it's called in integral systems land. Okay, so this tells us at the very least, for differential equations, we want to understand, what do singularities look like? How do we construct their moduli spaces? We can handle even say they ought to be algebraic geometric objects, but we actually need to do some work to say that they are algebraic geometric objects, and so forth. Okay, so the first thing we need to look at is what is the Lax pair going to look like? And there's another kind of Lax pair that has been understood, is we can look at difference equations. So I believe some of the discrete Pain-Levé equations have been known for quite a while to have difference Lax pairs. So this is what a difference equation, an ordinary difference equation looks like. And A, again, is going to have rational coefficients. So let's say it's an n by n matrix with rational function coefficients. If you like, you can pretend K is C. It's actually nicer for many purposes to allow K to be Q. And in fact, there's some parts of the theory that I can only prove by allowing K to become finite. But for the most part, you can pretend we're characters of 0. And especially for ordinary difference equations, it's kind of weird if they're not characters of 0. Okay, whoops. Okay, how did I skip back that far? Anyway, so this is what a difference equation, an ordinary difference equation looks like. And okay, what does it mean to be singular? So a singularity is a local obstruction, or let me just say it's an obstruction to having a local basis of holomorphic solutions. More precisely, it's an obstruction to the existence of a matrix M holomorphic near some point Z naught, such that M of Z plus, or near an orbit of point Z naught, such that M of Z plus 1 is equal to A of Z, M of Z, and the determinant of M is invertible. Or more precisely, the inverse of the determinant of M is also holomorphic. Now, if you think about it, this is what we meant by singularity in the differential case. Because any point that was not one of our singular points, we had this basis of solutions. And but we started with a matrix form of the equation. So each one of those two solutions we had were both vectors. We can turn that into a 2x2 matrix for the second order equations. And that 2x2 matrix, because we had a basis of solutions to start with, and I mean, it's not just a basis of solutions. It's the values of the solutions at those 2 points are linearly independent. And so we get this invertible matrix. The value at that point is invertible and satisfies the equation. So if you sort of put derivatives instead of z plus 1, this is exactly what we mean by a non-singular point, is that there exists such a matrix. And so a singular point is one where there doesn't exist such a matrix. And in general, then, different singularities corresponds to different analytic behaviors of the equation, or at least local behaviors of the equation. To be really precise, they correspond to different formal behaviors of the equations. So here, of course, we can turn this into a purely algebraic thing by taking our matrix to live in GLN of K double bracket Z minus Z naught, so power series, and really formal power series, they don't have to converge. And then we just ask for, and then we just use this equation to sort of extend it going on. And then the condition is that they should all be you have coefficients in the appropriate power series ring, and the inverse of the determinant should also be in that. Okay. So this is what we mean. And further, we see that a singularity has 2 flavors. So the first one is if Z naught is in K, it's a finite point, then and A either has a 0 or a pole at Z naught. So so okay, what I mean by pole is easy. I just mean it has one of its coefficients has a pole. And it's easy to see that as we carry along our function, when we cross through Z naught, even if it was holomorphic before even if it was holomorphic at Z naught, it's not going to be holomorphic at Z naught plus 1, or sorry, Z naught minus 1. And what I mean by having a 0 is that A inverse has a pole, and you just carry along, you just apply the difference equation in reverse, and see, and again, you find a point where even if it's holomorphic going in, it's not holomorphic going out. So this is the first kind of singularity. And conversely, if both A and A inverse are holomorphic at Z naught, and everything in the orbit of Z naught, then your equation is non-singular at Z naught. Okay, the other type of singularity is at infinity. So now we're basically asking for a matrix with coefficients in formal power series in 1 over Z that satisfies the equation. And well, here we could just say, okay, well, M is in GLN of this formal power series over Z. And we notice that Z goes to Z plus 1 actually acts on this ring. And so M of Z plus 1 is also in this particular group. And then we can say that A of Z is M of Z plus 1, M of Z inverse. And so this tells us something about what it has to be if this is going to happen. In particular, the first thing we note is that M and M of Z plus 1 are the same at infinity, because 1 over Z and 1 over Z plus 1 both vanish at infinity. So the limit as Z goes to infinity of A of Z has to be 1 if we're going to be smooth, if we're going to be non-singular at infinity. And moreover, well, 1 over Z and 1 over Z plus 1, they don't just agree at infinity, they agree to second order at infinity. 1 over Z plus 1 is equal to 1 over Z plus big O of 1 over z squared. And so in fact, we also have that A of z is equal to 1 plus big O of 1 over z squared. And so our equation is singular at infinity if A of z is not 1 plus big O of 1 over z squared. And this turns out to be an if and only if you can, again, well, basically you just start with anything and you just try to solve the equation. And what you realize is that as long as this condition is satisfied, you can sort of solve order by order for what the solution of the equation is, and you get a full basis of solutions. This is basically the same kind of thing you would do for the power series method for solving linear differential equations. Okay, so this is the two flavor singularities of an ordinary difference equation. Okay, and now we can ask, well, okay, suppose we're given an equation like this, which is second order, and is, well, for annoying technical reasons, making it smooth at infinity or non-singular at infinity is usually not the right thing to do. There's a little bit of basically line bundliness. So we have it, so it's A of z. Instead, we have it be 1 plus, let me call it theta, because it's essentially coming from a line bundle, plus O over z plus big O of 1 over z squared. So it's not quite non-singular at infinity, but it's very close. And in particular, if you rescale by z to the theta, you get something which satisfies a much more complicated equation, no longer rational, but now actually is holomorphic at infinity. So it's very, it's sort of very uniformly singular at infinity. And it has 8 well, let's see, not 8 singular points, but well, it will be 8 singular points, but it has 4 poles and 4 zeros. And here we note that theta is a function of the poles and zeros. Okay. And which again, you can see this by taking determinants. And you see that, okay, the determinant of A is 1 plus 2 theta over z. And the determinant is also, a rational function that vanishes where you have zeros and has poles where you have poles. And and then you say, oh, well, it also has to be 1 at infinity. So that gives you the scale factor that would otherwise be there. And so you just solve that and say, yeah, okay, this is what A has to be. This is what the determinant of A has to be. And that tells you what theta is. And you find that theta is actually a linear function of the poles and zeros. Okay. And so this given that I had 4 poles and 4 zeros, actually, let me again start with a simpler version. We have 3 poles and 3 zeros. And this has, again, a 0-dimensional moduli space. That is, if I tell you where the 3 poles are, where the 3 zeros are, and that it's essentially non-singular at infinity, that uniquely determines the equation up to a change of basis. And what is this equation? Well, for those of you who know hypergeometric functions, we have it. If you sort of play around with some rescaling, you can sort of kill off 3 of the parameters, or I guess 2 of the parameters, and you're left with 3 parameters, A, B, and C. which are essentially 3 of your exponents when you forced 2 of them to be 0. And then the 4th, and then the 6th exponent, of course, is determined by the others. Well, one of the things you can do to a Fuchsian equation that has given exponents is you can shift the exponents by 1, and that doesn't change the analytic structure of the equation. So in particular, and now there's a global thing, so we have to shift 1 up or 1 down. But if you do that, you don't change the monodermy of the equation. Because here, we're in this case where the monodermy, again, is rigid, you do the dimension count. So you don't change the monodermy up to a change of basis. Which means that if you take your equation, or you take your solution or at a nice point, and multiply and divide it by the solution of the modified equation, where we move 2 exponents. Or if you want to go crazy, you can move all of the exponents by integers as long as they still add up to the right thing. So that gives you m hat. So it solves a completely different equation. But here's the thing. If you take this matrix and move it around in the complex plane, as long as you divide it on the correct side. Sorry, my biggest weakness as a mathematician is if you give me 2 choices, I will never remember which one is right. Even if it's not even a 50% chance, but unless I try to take that into account. Okay, so you take your 2 solutions of these 2 different equations, and you ask what happens when you move around. Well, the thing is, the monodermy is the same. And it was the same up to a change of basis, but we can choose our basis in such a way to make it actually the same. At which point we find that this is monodermy invariant. Or in other words, it's single valued. Moreover, because we had this, there's Fuchsian equations, we had this asymptotic information about our 2 matrices, and because we know the monodermy is the same, we can match that up. And so we're hitting the big solution of one with the big solution of the other, the small solution of one with the small solution of the other. And so what we find is that the single valued function is bounded by a polynomial around one of our singular points. And in fact, we can be even more precise about what polynomial is bounded by, but for this statement, we don't need that. What we find is that it's rational. So in particular, what we see is that if you take this Gauss's hypergeometric equation with its 3 singular points and 6 exponents, and move them in various ways, keeping the sum condition correct, the new solution, or there is a new solution, which is a rational matrix times the old solution, the solution of the original equation. Okay, even better, is what happens if you just fix one such transformation. Take a very simple one. Let's say we take the 2 exponents at one point, move 1 up, move 1 down, and then keep doing that. Well, what you find is that this rational function of z turns out to also be a rational function of that parameter. And so this gives you something called a contiguity relation. And if you've chosen which shift you're doing correctly, the contiguity relations of the hypergeometric equation look like this picture. They're linear equations, they have 3 singular points, but they're linear difference equations. In particular, the contiguity relations of the hypergeometric equation are rigid difference equations. Okay. All right, and you can do the same thing now with for more singular points. So you have m zeros, or let's say 3 plus m zeros, 3 plus m poles, and should be 2m dimensional if you do all the dimension counting. I mean, a common feature that always arises here is there's always one redundancy. So you do the dimension count and then argue why you should why you're allowed to add one. Okay, so that's the that's sort of the simple version of this. And then there's another type of equation that arises. You can take a Q difference equation, where now, instead of adding 1, you multiply by Q. But again, the coefficients are rational functions. And then there is something called a Q hypergeometric function. And it satisfies a second order Q difference equation. And that second order Q difference equation is rigid. And it turns out in this case, the contiguity relations are also the Q hypergeometric equation. And so it's nice regaining a little symmetry. But it has the same sort of flavor. There are 3 zeros, 3 poles, and it's almost but not quite non-singular at, well, 0 and infinity now are the two fixed points where it's more complicated to be, where being non-singular is more complicated. Okay, now there's an observation which is relatively recent in the picture, although it's certainly hinted at in Sakai's hierarchy, and I think that slightly predates Sakai in that case. But there's another kind of hypergeometric function. It's sort of where it's coming from is somewhat easier. It's actually relatively easy to explain from an algebraic geometric perspective. What are we doing with these difference equations? We're translating by an element of a group scheme, particularly an element of a one-dimensional group scheme because we have one parameter. So the idea is we replace the additive group or the multiplicative group, i.e. ordinary or Q difference equations, by a general commutative, one-dimensional connected commutative group scheme. Now, of course, if you're familiar with group schemes, you realize that there's not a whole lot more. So in other words, we have the additive group, we have the multiplicative group, or we have an elliptic curve. Okay, and so this gives us an elliptic difference equation. Let me say it's z plus q now. But now A of z is a matrix over the function field of the elliptic curve. And Q is now a point of the elliptic curve that we're translating by. Okay, so this is another kind of equation that we could consider. Now, there's already a little hint that there's something more complicated going on. Because I talked about Gauss's hypergeometric equation and the contiguity relations. But Gauss's hypergeometric equation is not the most general ordinary hypergeometric function that still has nice properties. And particularly, there's a theory of elliptic hypergeometric functions. But if you start taking limits of them, you see these more complicated versions of hypergeometric functions. Like things that are like very well poised or balanced or what have you. Lots of extra adjectives to explain why you have this very high order thing that a priori satisfies an 8th order equation or something, but it still ends up being nicely behaved and like evaluates to a nice function or satisfies nice transformations or what have you. And so there's a little bit missing, but we'll see where that comes from, because it'll actually be hinted, will be led to that by the geometry. Okay, so let me rephrase one of the original questions. Given a type of equation with specified singularities, how can we understand, or how can we construct or understand what have you, the corresponding moduli space? So in other words, what I mean by this basically is to specify, it's an elliptic difference equation or an ordinary difference equation or a Q difference equation or a differential equation. And if it's a differential equation, it could be a differential equation living on a curve. That sort of can be made sense of. How do we understand the corresponding moduli space? Okay, and this is where things get tricky. So I mentioned earlier that in order for the isomonotomy flow to really be flowing on some nice thing, we have to include, in the Pendle A case, we have to include some things that are not matrix equations. So how do we, well, it's not quite compactifying yet, but how do we partially compactify Fuchsian equations? Because we want something that's going to be a good enough moduli space to explain our flows. Well, okay, so this is where we get to the very little amount of differential geometry. A differential equation, so a matrix differential equation, or this linear difficu, is a connection on the trivial vector bundle. And since we're doing algebraic geometry, I'll write it as a power of the structure sheaf. Now, because we're doing algebraic geometry, what it means by a connection is likely less familiar, but that's what a matrix form differential equation is if you think in differential geometry terms. We have this vector bundle, and we have this connection on the vector bundle, and that's, this equation really is specifying a connection. And so to compactify, we turn our vector bundle, our trivial vector bundle, into a non-trivial vector bundle, and that gives us a bigger moduli space. Now, of course, when we do that, if we're doing algebraic geometry, it better be flat. So this has rank n, and to be 0 if we wanted to actually be filling in the gaps of an ordinary matrix differential equation. Now, this already tells us that, well, okay, this may not be quite the right thing to do in general, because we might want to allow connections where the vector bundle is never trivial in our family. And we'll see later that there actually are some funky, if you will, lax pairs for Pain-Levé, some new lax pairs for Pain-Levé, where the vector bundle is never degree 0. It's for instance, it might be rank 4 degree 1 is one of the examples. And standard disclaimer, don't ask me to write it down because actually I don't think it ever has been written down. But the theory tells us it exists. Okay, so this gives us a toy problem. If we're going to understand this problem in general, we need to understand the differential case. So we need to construct a nice moduli space of connections, of meromorphic connections on vector bundles with specified singularities. Okay, now we're going to very briefly digress into post-Hartshorne algebraic geometry, if you like. There's a theory out there that tells you how to construct moduli spaces. It's called geometric invariant theory. And it's beautiful theory, incredibly powerful, and extremely hard to apply. Or more precisely, it's actually relatively easy to apply. What tends to be hard is actually interpreting the answer it gives you as an actual moduli space. So basically, the general theory is you basically start with a projective variety and an action of a nice group on it, and it tells you how to construct a well-behaved quotient. Now, this tends to be, the way it actually works is you throw some stuff away, and then you say, okay, some orbits, even if they're different orbits, are actually equivalent anyway. So you do this, you have this slightly weird equivalence relation, but it gives you a quotient, and that quotient is a projective scheme. So everything's great. Or quasi-projective if you start with something quasi-projective. So it's all fine, but because you tweak the equivalence relation, there's always this problem of, okay, well, firstly, you threw some stuff away. Well, what did you throw away? You want to at least be able to explain which isomorphism classes got thrown away. And secondly, you need to explain in a moduli theoretic term, in a geometric way, which new things are equivalent that weren't before. And this gets complicated by the fact that there's choices to be made during this process, and those choices affect the new equivalence relation, both what gets thrown away and what things are equivalent. So there's this theory, but it takes a lot of work to apply in a given situation. So this is a problem. And this was sort of a big sticking point for quite a while. I mean, basically the only ways I was able to get information about for special cases was where basically I could just directly do the geometric invariant, or I could actually write down explicit equations, which you can almost never do in moduli space theory. But I can sort of write down explicit equations and say, okay, well, I actually can recognize this explicit equation as cutting on a rational variety. And so I could say at least, hey, this is a rational space, and try to go from there. But it's very limited. In particular, I could only make it work for second order things. So this is an issue. So how do we deal with this? Well, the standard rule in math when you're approached with a hard problem is, okay, either you make it harder, sometimes that's the right thing to do, but the other thing is you try to find some way in which somebody has already solved the problem for you. So in particular, we'd like to reduce this to an already solved problem. We can't quite do this, but we can get close. And so the basic idea if we relax things, we can actually get a dictionary, or we get a translation from, well, now I'm going to put scare quotes, because they're not actually going to be equations anymore. That's the big thing we're going to lose. But what they're going to translate to are completely familiar algebraic geometric objects. In particular, they're going to be sheaves on projective surfaces. And I should say now, so this is sort of the key thing when I talk about the geometry of differential equations. And when I say non-commutative, it turns out that if you can get rid of the scare quotes on the left, so talk about actual equations or actual connections, as long as you're willing to do something more complicated on the right, namely allow non-commutative projective surfaces. But this definitely is a much more complicated thing. So let me put that off for a long time, talking about the non-commutative picture. Okay. So how do we make this work for connections? So there's a notion of a Higgs bundle. And what this is it's basically if you say, okay, I have a matrix form differential equation, and I don't like connections because I don't do differential geometry. Or if you're doing algebraic geometry, there's a way of talking about connections, but they involve non-reduced schemes, and let's try to avoid those for as long as we can. So I don't want to talk about connections, but I do want to compactify my modular space. So the way to do that is we say, okay, well, I have a matrix. A matrix is a map between vector bundles. So my matrix is, it started out as GLN of K and C, but we do say, okay, infinity is something special. There's this funny thing going on in infinity, and it means that actually the degree is not quite right at infinity. We need to take that into account. And so what you find is that A is not a meromorphic, is not an automorphism of Z, of our vector bundle V, or sorry, of our trivial bundle. But rather it's a map, or it's a matrix where the coefficients are differentials, which of course makes sense. It's dV equals AV. And since V is an actual thing in a vector bundle, and dV we're trying to pretend isn't something more complicated than that, is a vector of differentials, A had better be a matrix where the coefficients are differentials. Okay, but now we can turn this into something on a more general vector bundle. Namely, it's a map from V to V tensor omega. And I should be a little careful here. Oops, sorry, my eraser's too big. The eraser was still too big. Oh, well, anyway, of course, there are meromorphic functions, but that's fine. So this is such a map of vector bundles is called a Higgs bundle. So in particular, the actual Higgs bundle is, I think, the vector bundle V together with the rational map V to V tensor omega Z. Okay. And in fact, often in the literature on Higgs bundles, they don't even allow it to have poles. They just, because they're usually looking at higher genus curves, and then you don't need to allow, you can have them without allowing poles. But for most of for what we're doing, actually, the most interesting case is always going to be C equals P1, and then we need poles if we want to have a map like this. Okay, so this is a Higgs bundle. So how do we turn this into something a bit more familiar? Well, the first thing we can observe is that, okay, the problem is we have these poles and we have these zeros. And okay, the zeros are fine, but the poles are a little annoying because, well, we need to actually say where they are. Now, there's sort of a lazy thing we could do. We could just say, okay, well, replace omega c by omega c minus some divisor, or sorry, plus some divisor, and just allow poles along some divisor. And we can do that. But the annoying issue is that it sort of that over allows the poles. Because and in figure, it doesn't give us a good way of getting a handle on more complicated poles, what the structure is when it's the second order poles or so on. It's a very crude kind of thing. And it turns out there's another way of sort of encapsulating the information about where the poles are. Namely, we can write A. Well, we factor A as a product of B0 and B infinity inverse, where B0 goes from V to W, some other vector bundle, and B infinity goes from V tensor omega C to W. And while it's clear, so the first thing to observe is that any meromorphic matrix has a factorization like this. Because after all, we can factor through V tensor omega C twisted by the appropriate line bundle. So we can always do that. So we can just take B infinity to be, the V tensor omega C maps to omega C twisted by D. But okay, so now the problem is there's too many of these factorizations. But there's a unique factorization which we can get by taking the minimal vector bundle W. And it turns out there is a canonical minimal vector bundle W. Okay, let me set that aside for the moment, why there's a minimal one. And let me also slightly tweak things. So I'm just twisting B infinity by, inverse of the sheaf of differentials. This is perfectly fine. So this is now how we're specifying it. And as I said, this is now a unique thing coming from A. Okay, so let's combine them into one piece of information. So we just take the direct sum that gives us a matrix B, where now, of course, its coefficients live in some rank. It's basically, it has coefficients in a rank 2 vector bundle, but we'll temporarily ignore that. Okay, so this is our description. And now we make the observation that this, well, we can write this tensor product with W of this rank 2 vector bundle as a composition of functors where rho is a map from a surface to C. So the natural projection where X is the ruled surface corresponding to this rank 2 vector bundle. And this is just coming from the fact that, by construction, the direct image of the pullback of the structure sheaf of C is the rank 2 vector bundle you use to construct the ruled surface. I should caution, I might need to dualize this rank 2 vector bundle because, again, give me two choices, I will never remember which one is right. But this is basically what's going on. And so we can write this now as B going from V to rho lower star, rho upper star, W. But by adjunction, this is a map from, you can think of this as a map from V, rho upper star of V to rho upper star of W. Okay. So now we're closer. We actually have something on a surface. Okay. So, oh, and sorry, this is not quite right. We need to twist by the relative O of 1. Okay. And now again, I'm going to cheat and twist by a line model. And actually, let me, rather than say the relative O of minus 1, let me pick a section of my surface and actually twist by that divisor class. Okay, so this is what our matrix B is. And now we're going to take B and say, hey, it's a map of vector bundles. And moreover, if you sort of trace through what's going on, it has to be injective, or else our equation is not going to be an equation. So we can take its co-kernel. So let me call that M. And this is a sheaf on this ruled surface. And we then have the claim that M uniquely determines B up to the usual change of basis. Okay, why is this? Well, we have an exact sequence. A short exact sequence, no less. And if somebody hands you a short exact sequence, the first thing you should always do is apply a functor to it and look at the long exact sequence. So we're going to apply the direct image to that. And what are we going to get? Well, here's the thing. We have this section. On every fiber, it meets every fiber once. So O of minus S on any fiber is O of minus 1. Rho star V is a trivial vector bundle on any fiber. So when we twist it by minus S, it becomes O of minus 1 to that power. And so rho star V minus S becomes 0 when we apply the direct image, because O of minus 1 on P1 has no global sections, no higher direct image. Its Euler characteristic 0 is killed by the direct image. Right? Well, on P1 is killed by global sections and derived global sections. So taking sort of relative cohomology kills this first term. And thus we find that W is rho lower star of M. Similarly, V is up to some non-canonicalness that you can make canonical, but I would have to be more careful to do that. Is R1 pi rho lower star of M twisted by minus S. And again, you look at this and you say, okay, well, if we twist by minus S, the W guy is going to get killed. And this is O of minus 2 in every fiber. And O of minus 2 is non-canonically the sheaf of differentials on P1. And so modulo that non-canonicalness, you get this isomorphism. And then the slightly more tricky thing is where you recover the matrix from. But the point is, once you, but again, you look at this and you say, okay, I know what this guy is. And I know there's a map. So, you can recover. So this you can either recover as the kernel of that map, and then you can recover this as the kernel of that map, and then say, well, hey, it's the kernel of that map. It's kind of a canonical thing, but I know the kernel of that map has this form, and so that lets you recover V, lets you recover B. We can apply a junction. Well, sorry, you twist, and then we apply a junction to get back our matrix on our original curve. That's the same as this. And then we split that up. And then we take the appropriate ratio, and that recovers our equation. So this gives us an injection from equations to sheaves, and we can recover and we'll talk more about this later. This works for typical one-dimensional sheaves. So the one thing we know is that V and W had the same rank, and so therefore M has rank 0. So it's a one-dimensional sheaf on the surface. And there's some annoying issues that arise, but in some general sense, in some very general sense, one-dimensional sheaf can be, we can turn the crank backwards and recover a Higgs bundle. And that's sort of an equation. And I think this is the point where I should be stopping, because I think I was going to do 90 minutes a day, and now we're going to get into the, but then I have 30 minutes worth of questions. So I think this is where I'll stop lecture 1. Oh, I forgot to say at the beginning of this, please ask questions, especially those of you who are senior enough that you realize that if you don't know it, then probably most of the audience does it, and
Hi, Eric. Can I ask a question now?
Sure. Yes, we have entered the question period.
Good. So along the line of this very nice story, you mentioned the Q difference case fairly briefly. And you said that being non-singular is more complicated.
Well, it's basically the same sort of thing that's happening in the additive case. It's actually less complicated than the additive case, but there are 2 points. But the singularities again have two main flavors. So you can have a finite singularity, which just looks the same as a finite singularity in the ordinary additive case. Namely, it's a place where your matrix has a 0 or a pole. But at 0 and infinity, basically because those are fixed points of the translation of the automorphism you're using to build your equation, what it means to be singular is more than just having a 0 or a pole. Basically, you need to beat the identity to first order in order to be non-singular. This is an example of the kind of phenomenon that in this picture, things always get simpler the more general they are and the harder they are to write things down explicitly, the simpler they get. Because at the elliptic level, there's no 0 or infinity. And so all you get is finite singularities.
Right. Now, I was just trying to relate that to what Birkhoff and Carmichael wrote down many decades ago for linear difference, Q difference cases. And they had further conditions to do with, not having Q multiples, Q integer multiples.
Right. So that gets into a question of, this is already something I was sort of gliding past in the Fuchsian case. There are bad things that can happen. In particular, if your exponents differ by integers in the Fuchsian case, then you can have situations where your equation actually collapses to something low order, or collapses to a simpler equation. Because basically if you take the hypergeometric equation and you multiply it, if you take the hypergeometric function and multiply it by z minus lambda, now it's going to be still satisfy a second order differential equation, and it'll still be Fuchsian, but that Fuchsian equation will have a singularity at lambda. And so you get this, there's this phenomenon of apparent singularities that can cause issues. Now, what that's going to translate to, now that I've talked about sheaves, what that's going to translate to is basically cases where your sheaves are reducible, and some of the components of the support of your sheaf don't actually correspond to equations. And so you can get some situations where and sort of removing that component makes your equation look simpler relative to this picture.
I see.
So that's going to happen for all of these situations. There's always this annoying possibility of apparent singularities. And so one of the things, so in particular, what you should, if you sort of want to really understand, I mean, if somebody hands you an equation and says, I want to understand where this fits in some hierarchy, the first thing you need to understand is to what extent it has apparent singularities. Now, one thing you can always do in this picture is you can always move all the singularities so that, if you take any given orbit, you can move all of the singularities on that orbit to one point.
Yeah.
I tell a slight lie in the symmetric case, which we'll talk about later, but roughly you can always move the singularities to one point. And once you've done that, that'll actually kill off any apparent singularities that are left. And so what it actually does encapsulate the singularity along that orbit. Now, the problem with doing that is that that's a slightly more analytic thing to do. In particular, if you deform Q, which things collapse is going to completely change.
Right.
If you take the same matrix and change Q. So you have to if you do have apparent singularities, you have to decide, are they really there and you want to sort of get rid of them before you deform your equation? Or are they just sort of an artifact of the fact that, it's hard to write things down sometimes. Maybe the only thing you can write down happen to have apparent singularities, and you really want to allow them to deform. And that's where you have to sort of make that kind of decision. And one thing I should note is, for instance, if you look at the orthogonal polynomial solutions of these equations, well, okay, those don't have apparent singularities. They have, but they are reducible.
Yeah. And
how reducible they are but sort of the farther into the hierarchy, the farther away from the actual linear weirdness you get, the harder it is to see that they're reducible.
Yeah.
Okay. And so really, if you want to, if you should really sort of pretend they weren't reducible when you try to deform it. Yeah. Because you're allowing them to be, and that actually, if you do that to the elliptic by orthogonal function thing, that does give you the lax pair for elliptic Pan-Levy.
Okay.
If you do this sort of general thing. But we'll see later, and everybody's already familiar with one case of this. There are integral transforms.
Yes.
That can turn equations into other equations.
Yes.
And if you do that, if you do the correct linear transformation, integral transformation to this reducible thing, you can get something which is not reducible, but has an apparent singularity.
Right.
So there are indeed cases, so there are special cases of the so-called hypergeometric solution, which is, the only thing we can write down in complete generality for these, or at least completely nicely for these Pan-Levy transcendents that really do have apparent singularities, but we do want to pretend that they aren't actually apparent singularities you can deform. But we'll talk more about that later when I've had a chance to get to the other types of equations and things like that. Thanks. But yeah. So there's two main references, and Akane has helpfully provided one of the archive numbers. So the main one is 1307 4033, which is generalized Hitchin systems on rational surfaces. Although it actually does talk about some stuff that's not on rational surfaces, but it mainly focuses on that, which is also the interesting case. And then the other one is 1307 4032, which I think is birational morphisms, although it has a spoiler in the title. Birational morphisms, I think either on or of Poisson moduli spaces. So these are the main references. These don't have the non-commutative picture because I'm not going to be talking too much about the non-commutative picture. But if I have time, day 9 or something, and I feel like talking about the non-commutative picture, I'll give the reference then. But this is the main thing. And then there's some other references that may get temporarily touched on, but I'll give them when they get temporarily touched on. So those are the main papers of mine that are references. And of course, as I said, I'm going to be assuming sort of basic algebraic geometry, i.e. basically either Hartshorne or Vakil, were sort of the two main accessible references. If you're really masochistic, you can go for EGA. I do not recommend it, but if you're really masochistic, you go for the Stacks project. But let's not. Anyway, so Hartshorne or Vakil are sort of the two big things. And when I say Hartshorne, there's like these two sections at the end of Hartshorne which are on curves and surfaces, and I definitely use those. But and blowing up, of course, is the biggest thing that's less familiar that will get used later on. But anyway, and beyond that, of course, I've already done a little bit of derived functors and the usual homological algebra stuff. But it's going to be very hard for me to avoid those. So yeah, I should say it's a shame. Well, it's certainly a shame for me that this can't be in person because I have fond memories of the last time I was at RIMS, and but also the original plan for this, there was going to be like a second hour lecture every day. There would be some other lecturer on something vaguely related, and there would be informal sessions in the afternoon. But sadly, I will be asleep in the afternoon, so that's not going to work. But I encourage any of you who happen to be in the same location to organize your own informal sessions in the afternoon or something. It may be a little premature now, but at some point, when I've actually told you how to do certain computations, you may want to actually try to do more computations and organize informal groups to do that. I suppose it may be even possible to do that over Zoom, or I don't know how well that would work, but those of you who are all in sensible time zones that are not Pacific time can try to do that. But
sorry, I didn't catch what you said about Hartshorne. Was it the last two chapters?
Oh, so basically, when I say Hartshorne, I really do mean like all of Hartshorne, including the last two chapters, which are on curves and surfaces.
Yeah. Okay.
Although when I say surfaces, I basically, it's going to be rational surfaces. None of these, or ruled surfaces. None of these crazy things like abelian surfaces and K3 surfaces. But
yeah. Okay. Thanks.
Yeah. Well, okay. I will say brief things about them, but I think mainly the brief things I say about them will be, I don't talk about them. But I'll say a little bit more about why I don't talk about them. But anyway. Yeah, I don't know. I don't remember if Vakil has analogous discussions. But I know he has a very thorough discussion of road surfaces and blowups.
This is his online notes?
Yeah, his online book, basically.
Yeah.
Yes, I think it has a name now, The Rising Sea or something. But
that's right.
Yeah. I've been using them since before they had a name. So
yeah.
But yeah, no, they're also, I find them a pretty good reference, not just expository.
Mm-hmm.
And probably better for actually explaining things than Hartshorne.
Yeah.
Oh yeah, there's another book that I like for Eisenbud and Harris. I think has good exposition of why you do some of the weird schemey things. Yeah, we'll definitely be doing weird schemey things here, so it's not a bad one to look at. In particular, I said something earlier about avoiding non-reduced schemes. Sadly, we will not be able to avoid non-reduced schemes forever, but so we will have to get into the actual algebraic geometry and not just varieties.